Hi guys, welcome back to YouTube channel Chemistry Live UGPG. So today we are going to talk about alcohols, phenols, ethers and epoxides CC6 paper unit 2 lecture 3. So this will be highly useful for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So today we are going to talk about Bouvaelt-Blanc reduction, preparation and properties of glycols, oxidation by iodic acid and lead tetraacetate, and Pinacol-Pinacolone rearrangement. So let's talk about preparation of a glycol, ethylene glycol. So this is the structure of a glycol, 1,2-ethane-diol. So CH2OH, CH2OH. So we can prepare the glycol from ethene. So we can either react with potassium permanganate or osmium tetroxide. So we get ethylene glycol. Similarly, we can treat with this chlorohydroxy compound reacting with sodium bicarbonate, giving rise to 1,2-diol. Similarly, ethene can react with oxygen and silver, giving rise to this epoxide, which upon treatment with a hydronium ion, giving rise to 1,2-diol. Similarly, bimolecular reduction of acetone with magnesium. So you will end up with this magnesium complex, which further treatment with water, giving rise to this 1,2-diol, that is called Pinacol. So here is the mechanism. So ethene react with KMnO4, giving rise to 1,2-diol. So this pi bond of ethene will attack to this oxygen, and this Mn double bond O will break on manganese, and Mn double bond O will attack to this carbon. So here you have a 5-membered unstable complex, which upon further treatment with water and hydroxide anion, giving rise to 6-diol. Similarly, alkene can react with osmium tetroxide. So pi double bond will attack to this oxygen, and this osmium double bond O will attack to this carbon. So again here you have 5-membered unstable complex, which on treatment with water gives 6-diol. Next is properties of glycol. It is a colorless syrupy liquid, boiling point 197 degrees Celsius with a sweet taste. It is miscible with water and ethyl alcohol. Then next is chemical properties. So it gives the reactions of a primary alcohol. So ethylene glycol react with sodium, giving rise to sodium derivative. Then further treatment with disodium derivative. Similarly, ethylene glycol react with PCl5. It gives chloro derivative plus POCl3 plus HCl. Similarly, ethylene glycol react with HCl, giving rise to chlorohydroxy derivative, and further reacting with HCl, giving rise to dichloro derivative. So next is it can react with HiO4, iodic acid. So ethylene glycol can give rise to formaldehyde 2 equivalent. Then this reaction is called Mann-Laprade reaction. So oxygen lone pair of ethylene glycol will attack to this iodine, and this double bond will break on oxygen. So as a result, you will have this intermediate, and here loss, this OH will break on this O plus, loss of proton, you will end up with this intermediate. So again, oxygen lone pair here will attack to this iodine center, and this double bond will break on oxygen. So as a result, again you have this 5-membered protonated intermediate, and loss of proton here will give rise to this complex, which is unstable. So here simultaneous bond breaking and bond making takes place, giving rise to in this fashion. So this bond will come here, this bond will go here, and this bond will break on iodine. So as a result, you get 2 equivalent of formaldehyde plus HiO3 plus water. So this is the structure of 4-iodic acid, HiO4. Similarly, ethylene glycol can react with lead tetraacetate, PbOAc whole 4. It can give rise to 2 equivalent of formaldehyde. So here is the mechanism. So oxygen lone pair of ethylene glycol will attack to lead, and it will kick out OAC as OAC minus. So you get this protonated species here and loss of proton here, giving rise to this species. So again oxygen lone pair will attack to lead and it will kick out OAC as OAC minus. So again here you have 5-membered complex or intermediate. So this is unstable. So here simultaneous bond breaking and bond making takes place. So this bond will come here, this bond will go here, and this bond will break on lead. So as a result you get lead acetate plus 2 equivalent of formaldehyde. The next reaction is dehydration of 1,2-diol. So this 1,2-diol ethylene glycol undergo dehydration in presence of zinc chloride. So you get this unstable compound which tautomerizes to give rise to acetaldehyde. So here is the mechanism. So oxygen lone pair will attack zinc chloride. So you have this protonated species. So what happens here? The simultaneous bond breaking takes place and bond making takes place. So it will come here and this bond will break on O plus. So as a result you get this enol. So which tautomerizes, giving rise to acetaldehyde. Similarly, ethylene glycol upon heating at 500 degrees Celsius, it loses one molecule of water, giving rise to ethylene oxide, epoxide. Similarly, ethylene glycol can form polymer. So just like pteryline or dacron. So ethylene glycol can react with 1,4-dicarboxylic acid. So giving rise to a polymer that is known as dacron. So next is Bouvaelt-Blanc reduction. So the ester can be reduced to alcohol in presence of sodium and ethanol, metallic sodium. So oxidation state here is 0. So this is an inexpensive substitute for lithium aluminum hydride or sodium borohydride reduction method. So the sodium metal serves as single electron reducing agent and ethanol as proton donor. So if no proton donor is available, so it will dimerize and that is known as SiO1 condensation. So let's see what happens in Bouvaelt-Blanc reduction. So sodium can transfer one electron to this carbonyl carbon and this double bond will break on oxygen. So here you can radical anion. So here is carbon radical and here is oxyanion. So O minus will take the proton from ethanol. So you get this hydroxy radical. So again sodium will transfer another electron to this carbon radical. So you have 2 electrons. So this becomes C minus. And so once this becomes carbanion, so it will take the proton from ethanol. So you end up with this derivative. So again when this OH bond will come here, it will kick out OR as OR minus. So you end up with this aldehyde. So again once you get this aldehyde, it will donate one electron to this aldehyde and this CO double bond will break on oxygen. So you have this radical anion. So this oxyanion will take the proton from ethanol. So you can have hydroxyl group. So again sodium will donate another electron to this carbon. So it becomes carbanion. And this carbanion will take the proton from ethanol. So you get this primary alcohol. So next is Pinacol-Pinacolone rearrangement. So this is the compound called Pinacol, 1,2-diol. So that is the hydroxyl groups at vicinal carbon atom 1, 2. So that is called vicinal diol. So this upon treatment with acid catalyst, so you will end up with this compound, keto compound, Pinacolone. This is known as 3,3-dimethyl-1,2-butanone. So let's see how that compound, that reactant is converted to product. So here this is the Pinacol. So hydroxyl group has oxygen has lone pair of electrons, so it can act as nucleophile. So oxygen lone pair will attack to acid electrophile H plus. So this becomes OH2 plus. So the OH2 plus, so this bond will break on OH2 plus. So you generate a carbocation. Once you generate this carbocation, so this CH3 group will migrate to this carbon. So as a result, you end up with this carbocation which loses one proton, giving rise to this keto, that is called Pinacolone. So this rearrangement lead to more stable carbocation yields the major product. So Pinacolone is used in pesticides, fungicides and herbicides. So please subscribe to our channel Chemistry Live UGPG. This is also available in the website www.chemistryliveugpg.com. For class 11th and 12th students, this is another channel Foundation Chemistry AV. So this is a simple step towards e-learning, making life better. Thank you for learning.